All right, so I think this is recording. Let's take a look at problem 6. They give us two functions and they ask us to find the domain of f, the domain of g, the domain of the function compositions. So let's start out finding the domain of each one of these, domain of f and the domain of g. Whenever you're finding the domain, you know that the default answer is the set of all real numbers. But you have to take a closer look at the expression and know that it's the set of all real numbers excluding any values of x that would cause division by 0, and also excluding any values of x that would cause us to take the square root or even root of a negative number. So if we look at f, we do not see any variables in a denominator. So I don't have to worry about division by 0. But I do see a variable that's underneath the square root. So this 3x plus 18 has to represent a real number that's greater than or equal to 0. Otherwise, we wouldn't be able to take its square root. Solving this inequality, we see that x has to be greater than or equal to negative 6. If I sketch that on a number line, I include negative 6 because it's underlined, and I shade to the right. Which means if I pick any number in the shaded region, then what I'll be taking either the square root of 0 or the square root of a positive number. Like let's plug in negative 6. 3 times negative 6 is negative 18, plus positive 18 is 0, and the square root of 0 is 0. I get an output. If I plug in some number that's bigger than negative 6, say 0, 3 times 0 is 0, and the square root of 18, that's a positive expression, 3 radical 2. And I could do that all day. If I plug in something like a negative 7, 3 times negative 7 is negative 21. Negative 21 plus 18 is negative 3. And within the set of real numbers, I can't take the square root of negative 3. So it makes sense that the domain of f is negative 6 or larger, from negative 6 to infinity. All right, so let's find the domain of g. When I look at g, I do not see any square roots like I did in f. I don't have to worry about taking the square root of a negative number. But I do see a variable in the denominator. And I can see by inspection that I want to avoid letting x be positive 3, because 3 minus 3 gives me 0, and division by 0 is undefined. So if I think about on a number line what that looks like, the entire number line is shaded except for the number 3. It's the only number in the entire set of real numbers that gives us a problem. G evaluated at 3 is undefined. It's the only solution to the equation x minus 3 equals 0. So in interval notation, the domain of G is from negative infinity up to positive 3, excluding positive 3, and from 3 to infinity. All right. Moving on for part C, we're being asked to find the domain of a function composition, f composed with g. And the one thing that I was always surprised about is that that's a new function. You get it by building it like an assembly line with these functions f and g. But I don't have to find the equation for f composed with g in order to find its domain. The reason is because I know how it was constructed. I can use the domain of f and the domain of g to determine the domain of this new function f composed with g without ever having to find the expression f composed with g. All right, so how is this function built? Well, we start with actually the second function, the second one listed, and that's g. We look to the domain of g, pick a value, plug it into g, and the output of g, we call it g of x. Well, that output of g now becomes the input for f, and the output of f of g of x. So two things have to be true to be in the domain of f composed with g. You know, when you give it a number, it has to make it through both functions. There can't be any hiccups. There can't be any situations where the output of either one of these is undefined. In order for x to make it through the function g, x has to be in the domain of g. And in order for this g of x to make it through this function f and to get an output, this g of x has to be in the domain of f. So if we look over here at the domain of g, we found the domain of g to be all real numbers excluding positive 3. And rather than writing it in interval notation, I'm just going to write it here in a shorthand notation that x cannot equal 3. That's just my scratch work. All right. Now over here, the domain of f. The domain of f has to be -6 or larger. Well, what is the expression for g of x? It's this rational expression, x plus 11 divided by x minus 3, and this has to be greater than or equal to -6. And these rational inequalities are a little bit challenging sometimes. First, we want to make our comparison against 0. So what we're going to do is add 6 to each side. But I need for these terms to have a common denominator. So I'm going to take this 6 and I'm going to multiply it x minus 3 over x minus 3. And this has to be greater than or equal to 0. So now these two fractions have the same denominator. We have x plus 11 plus 6x minus 18, all divided by this common denominator of x minus 3. I'm going to continue over here because I need this room. All right, so in this numerator, let's combine like terms. 1x plus 6x, 7x. And then 11 minus 18 minus 7. The denominator, x minus 3. And that has to be greater than or equal to 0. So we look at the numerator and denominator, and separately we set them equal to 0 and solve. X minus 3, 3 minus 3 gives us 0. So if x were allowed to equal 3, I'd be in trouble because 3 minus 3 causes division by 0. I exclude 3 from the domain. If I look at the numerator, 7x minus 7, and I temporarily set it equal to 0, this has a solution of x equals 1. Now, to determine whether I want to shade in the value for 1, well, I look to the inequality. And I see that it's greater than or equal to 0. It's that equal part that makes me shade this in. So these two numbers divide this number line into 3 regions, A, B, and C. If I pick a test point from each region and test it in this inequality, if it's a true statement, then every number in that region will be true, and I'll shade in that region. If it's false, every number in that region will be false, and I won't shade it. So let's pick an easy value from region A to test and see whether this inequality is true or not. In region A, I'm going to pick my test point to be 0. Well, then that's easy to do this arithmetic on. In the numerator, I have -7. In the denominator, I have -3. And yes, it's true that -7 divided by -3 is greater than or equal to 0. So I shade in this number line because it's going to be true for any test point in this region A. All right, so now what about in this region B? Let's pick a number that's easy to do arithmetic on. So I'm going to pick the number 2. And if I replace x equals 2, if I replace the x with 2, I want to look and see if this statement is true or false. So I have 7 times 2 minus 7, and then in the bottom, 2 minus 3. Well, 7 times 2 is 14. 14 minus 7 is a positive 7. The denominator is -1. And it's false that -7 is greater than or equal to 0. So I'm not going to shade in. I'm not going to use any point in region B to be in my domain. Let's pick a point that's bigger than 3 to see if it will be satisfied or not. So an easy number to pick in region C would be to let x equal 4. So in the numerator, we would have 7 times 4 minus 7, and in the denominator, 4 minus 3. 7 times 4 is 28. 28 minus 7 is 21. And 21 divided by 1 is definitely greater than or equal to 0. So that's in my domain. So we now have to describe this interval. So describing this interval is all real numbers from -infinity to +1, including +1, or excluding the number 3, 3 to infinity. We need to intersect this set with x not equal to 3. Well, look, here x is not equal to 3, so this becomes our final answer. Let's shrink this up. And I claim that the domain of f composed with G is the set of real numbers from -infinity up to +1, including +1, or, excuse me, from 3 to infinity, excluding 3. All right. I'm going to delete my work here just to give me some room for the next part. So what is the domain of G composed with F? Well, we don't have to find the expression for G composed with F. All we have to do is consider how it was built. We know that these function compositions, that a good analogy to think, a good way to think of these is to think of an assembly line. That you have one function being applied, then the output of that is applied to the next function. And the thing to remember is you start with the innermost one, with the second one in the list. So two things have to be true to get an output. This x has to be in the domain of f. And then f of x, the output of f, has to be in the domain of g. Otherwise, g of f of x will be undefined. So what is the domain of f? The domain of f was all real numbers greater than or equal to -6. What was the domain of G? The domain of G is all real numbers excluding the number 3. So what is the expression for f? The expression is the square root of 3x plus 18. We need to find the value of x that would cause an output of positive 3 and not let that happen. So to solve this equation, much easier than solving the inequality in part C, and that's we're going to square each side. If I square the left-hand side, I get 3x plus 18. If I square the right-hand side, I get 9. If I subtract 18 from each side, if I divide by 3, I get that f evaluated at negative 3 is going to equal a positive 3. I don't want that to happen because I know that g evaluated at 3 is undefined. It causes division by 0. So, in order to avoid g ever seeing the number 3, see, g, we don't want 3 to be an input. That means that we don't want negative 3 to be an input for f because it would cause an output that's undesirable. So the domain for this function composition g composed with f is the set of real numbers from negative 6 excluding negative 3 and from negative 3 all the way to infinity. So there's our domain for g composed with f. I hope that helps. If you have any questions, ask. It does take a little bit of time and effort to understand the domain of these function compositions. All right, talk to you later. Bye.